Good afternoon. Here yet again for another lovely session of CENG 3325 Structural Analysis. Let's see, this will be the 26th lecture in the video series, and today we're going to go over the final application I wanted to discuss of the force method for beams. So we have seen previously that the force method is very versatile. It can be used for solving deformations in statically indeterminate beams. I suppose you could use it for statically determinate beams as well, though I suppose it would be a bit of overkill for that. So you can use it to solve for deformation and stresses in statically determinate beams. You can use it to derive equations for bending moment and shear and rotation and maximum deflection for statically indeterminate systems and beams. But now I'd also like to look at a final application of it, and that is really to look at the effects of deflection on systems. So what do I mean by this? Well, let's think about this. Most of the systems, or most of the problems that we have looked at, most of the examples, have worked like this, in a very broad overview, of course. I have said, okay, well, here's our structure. Here's a structure such as our beam. And let's combine that with some loads that I'm going to put on it. And then in turn, so we have our structure, and we're going to put some loads on it. But then in turn, I'm just asking what kind of deformation comes out of this. So our input would be our loads and structure, you know, our geometry, our member stiffness, etc. And then we feed it into some various equations. We work through the force method. We do all of the things that we've been doing, and at the end, we'll get our deformation on the outside, on the back end. So deformation would be your rotations, your deflection, etc. But the great thing about the force method, unlike some methods, what is really useful about the force method is that it is reversible. So if you have essentially, let's think about this. On one side of this two-way arrow, you have your loads. On the other side, you have your deformation. But the key thing with this is that this is a two-way arrow. The equations work in both directions. So I can say, okay, well, here are the loads. I can give the math the loads and say, okay, well, here are the loads. What is it going to deform? But I can also do the opposite. I can say, oh, I don't know the loads, but I do know what it's going to deform, what the structure is going to deform, and then I can back calculate the loads. And so really, I love the force method just because it's so wonderfully versatile. I can either go from loads to deformation, or I can go from deformation to loads. And one area where this is particularly useful is areas where you're dealing with things like where you're imposing deformations on a structure. So cases where you impose deformation. Let's talk about some cases where deformation is imposed. Deformation or rotation is deformation either rotation or displacement is imposed. A few examples I can think of, and these are just a couple. I'm sure we could determine more. We could come up with more if we had some more time. And we sat down and really scratched our heads for a while. But two that I can think of are, first, you might deal with seismic design, where you're just suddenly moving the base out from under a structure. If you think of a structure, and so again, if you think of a structure here, maybe like a several-story building, it might be supported by the ground here. And when the ground moves, the mass of, if you think about an earthquake, in an earthquake, the absolute just the incredible volume of matter that is moving underneath your building is just monumental. You're talking about a, chunk of the Earth's crust that is miles thick, moving under a seismic wave. And so the ground is just moving in response to the seismic wave. And the mass of your building in relation to the mass of the ground beneath it is nothing. It is like a fly on the back of an elephant. It's nothing. In terms of, in terms of human scale, buildings and structures have large weights, but compared to the ground beneath them, the largest structures that humans produce are nothing compared to the mass of the earth that is moving during an earthquake. So, in other words, what I'm really getting at here is that in seismic loading, the ground does what it wants to do. If it wants to move over an inch, it's going to move over an inch. Your building or your structure is not going to noticeably affect the motion of the ground underneath it, because again, this chunk of the Earth's crust is wanting to move to the right, for example, at 1 inch or something like that. This chunk of the crust is going to move, and it's just going to carry the foundations of your building right along with it. And so when the foundation of your building basically just moves out from beneath it, what ends up happening is it passes by relatively quickly, and so suddenly your foundation is basically no longer underneath where your building is. So the ground moves to the right here as the seismic wave passes by, and the foundation actually moves to the right here, and the rest of the building hasn't caught up yet. So the building's foundation jolts over to the right, and the building itself, the rest of the building, is still hanging out up here, just unsure of what's going on. And this thing, the only way that the building can move to right itself on the new location is if stresses are transferred through the members to bring this back to equilibrium. But this is not a seismic design course, so we won't spend too much time talking about it, but that is definitely a case where you would have deformations imposed on a structure. And in regions where, now here in Houston, where I'm located at, we don't deal with a lot of seismic loading, but if you're in a part of the country or part of the world where seismic load is important, and you're doing any kind of structural engineering work, you are definitely going to be worried about seismic load. So, what else? Where else will deformations be imposed? Let's see, we could think of things like, now I could go for really niche examples, like things like rotating bridges and drawbridges and things like that, but the other example that really comes to mind, and so seismic loading, we could talk about that, but that is a very involved process, and you can to really learn seismic design properly, you could take an entire course on the matter, so I just want to illustrate it as an example of imposed deformation. I don't really want to work through an example of it because it is very involved. But the one example that I will work through today as an example, or the one type of loading, deformational loading that I will work through today, is the example of foundations, and in particular, foundation settlement. So, now, typically as structural engineers, or at least when we're talking about structural engineering or teaching structural engineering, we often ignore the actual ground underneath our structures. We just simply say, oh, it's a pin support, or it's a roller support, oh, it's a fixed support, and just say, it's good enough. That's the geotech guy's problem, not our issue. We're structural engineers, the geotech engineers can go play in the dirt, no problem. Well, they can deal with all the foundation stuff. But foundation settlement, this is a case where structural engineers don't have that luxury. So often in normal building design, the way things will work is the structural engineer will say, okay, well, based on the loads of the building, the wind, the rain, the live and dead load, all that good stuff, they will say, okay, well, I need foundation piers that can support a axial load of X and a moment of Y. And then they'll go to the geotech engineer and say, okay, here's my moment and here's my axial force. Design me some foundation that can support this loading. Well, in some cases you can't do that, especially if it is actually. So that's the kind of one-way process where you're saying, okay, here are the loads for my structure. Let's make the foundation. Let us make the foundation strong enough to resist those loads. But in certain cases, it's actually your foundation that is putting loads upon your structure. So, again, normally, it's the structure putting loads on the foundation. The structure puts loads on the foundation. But in some cases, hopefully, if you build a building or a house, especially if it's like your own personal house or something, I would hope not to encounter this, but sometimes it does happen. But sometimes it's the opposite occurs. Sometimes the foundation is what puts loads on the structure. And so everything's mixed up. So for example, maybe you have a foundation slab and there's maybe you build your house on top of this. So you have a great big concrete foundation slab and you have the ground underneath here. Okay, so let's think about this. Well, what I might do when designing this, I might assume that the ground underneath this can support a certain amount of weight, and maybe I assume that it can support a certain amount of pounds per square foot or newtons per square meter, whatever it might be. I'm make an assumption, an otherwise naive assumption, but again, when you're dealing with things like foundations, you almost always have to assume things, because you can't really know what's in the ground underneath you unless you dig out the entire thing. And so when I build a house, or when we build a house, or when people build a house, or any structure whatsoever, you're assuming that the ground underneath you will be able to withstand whatever load you're able to you will need. You're assuming that the ground will resist whatever load you need to put on it. Or more importantly, now not just a matter of whether it will have enough, but what I'm basically assuming is that the ground has a uniform capacity underneath. So if the ground was perfectly uniform, in other words, if I had imagine if under the, let's say I build a house, and underneath it, just by magic, there is perfect soil. In other words, let's say whatever soil I want, or whatever soil I assume there, it is exactly that soil for a ridiculous distance all around. Like if I am designing my foundation for clay of a certain consistency, magically there is clay, a mile in every direction around this foundation. Literally I could draw a radius and a mile all the way around. There is exactly clay of that consistency for as far as the eye can see, or for a mile all around, in a hemisphere all around my foundation. No inconsistencies. By inconsistencies, I mean there's no pockets of sand in there. There's no boulders. There's no rocks. There's no hollow points. There's no caves running underneath the house. I don't know, 1,000 other things. There's no again, often when we design things, we assume perfect soils. Well, of course, we often assume, we have factors of safety in there to hopefully take into account inconsistencies in the soil, but sometimes those do occur. Now, let's think about this. So maybe I design my foundation assuming an ideal loading, but what happens if I don't actually have ideal loading? So what actually happens if I don't have an ideal loading? Like, for example, let's say, unbeknownst to me, there's some sort of either a hollow or a weak point under one part of the structure. Oh no. What happens then? So I may have designed my house or my building or whatever it might be, assuming that I have perfect soil underneath it, maybe clay or sand or stone or gravel or whatever it is, to an arbitrarily large distance. But what if there is an inconsistency? Maybe if I assumed there was solid rock underneath my house all the way down, maybe there's sand here. That would be a weak point. Or maybe if I assumed there was sand, maybe there's a hollow here, or whatever it might be. When I'm talking about a weak point, we're talking about weakness in relation to the area around it. It could literally be a void full of air, or it could just be a location of soil of relatively weak structure compared to the things around it. So what's going to happen? Well, you don't have to be a structural engineer to realize that if you have one side of your foundation that has much less support than the other side, what's going to tend to happen is this thing is going to tend to tilt downward like this. So your foundation is going to tend to rotate, it's going to tend to deflect. Again, if I'm assuming uniform capacity across, I'm going to have deformation downward like this. And why is this important? Well, the thing is, deformation will produce loads in my structure. Foundation deformation foundation deformation produces loads in a structure. And this is also a case where you can see the interaction between geotech engineers and structural engineers, because I might tell the geotech engineer, the foundation engineer, to say, okay, well, I'm building the structure, and here's the distributed load or the point load and the moment that I need to resist, and go design me a foundation. And then the geotech engineer, who has all the knowledge of foundations and soils and all that good stuff, says, okay, I'll do that. But truth be told, there is no such thing as a perfect foundation. just like there's no such thing as a structure that can resist infinite load with zero deformation, or resist any load with zero deformation, no foundation is perfect either. So whenever you have, if you any foundation made of real materials, under some load it's going to deform. And so what the geotech engineer might come back and say, okay, the geotech engineer, again, when I say I want a foundation that can resist these loads, the geotech engineer might come back and say, okay, I have done this, but here is the actual way this foundation will physically perform. And what I mean by that is, yes, this foundation is strong enough to resist the loads that you have given me, but it is going to deform this much. So make sure the rest of the structure won't be harmed by those deformations. So we could, now I might reply back and say, no, that's too much. I don't want that much deformation. That's not possible. I insist on almost zero deformation. I want, a thousandth of a millimeter of deformation or something insane like that. And the geotech engineer will promptly reply, you're insane. At that point, you're better off building a bunker than a building, because your house is basically, or our structure now has so much concrete, it's basically a bunker, and you might as well just live in a mountain at that point. So anyway, wow. So if you're not careful with deformations, your buildings will start approximating mountains, so we can't really do that. So what your foundation engineer might come back and say, again, yes, here are the loads, but on considering the loads and considering both the loads and the variability in the soil, make sure your structure is able to withstand settlement of X amount of length. So that's, so many centimeters, so many inches, whatever it might be. So the way you double check that, or the way you make sure that's okay, is that you then feed those deformations back into your structure. So the foundation engineer might say, okay, maybe this end of the structure, depending on, the foundation engineer, again, does not have perfect knowledge. They really don't know if there are voids here, or they don't really know. There are techniques to sample soils, of course, but even if you do soil sampling, there's always a chance for variability. And so maybe they say, well, maybe the right end of this foundation can settle up to 2 inches. Make sure make sure the rest of your building is able to withstand that much deformation, or we'll make sure the foundation slab itself is able to withstand that much deformation from this end to this end without cracking. Okay, that's all well and good, but the point is that I really want to get at is that often the foundation will deform the way it wants to, and then we will take those deformations as loads. So for foundation design, we often consider deformations as loads in and of themselves, or as inputs. Or maybe I could say for foundation design or interface, or structure interface, we often impose loads at some point in a foundation. Impose loads at some point on a foundation, and then look at what kind of stresses develop. A foundation, and then investigate what kind of stresses develop. Alright, so with that, I want to get to the main design example for this lecture. So let us consider this, and I have a rather long problem statement, and we're going to investigate this in long form, again using the force method. Given a concrete foundation pier, let's get this, or a concrete foundation beam. A concrete foundation beam has a width of 12 inches, has a width of 12 inches, and a depth of 24 inches. we often build beams into our foundations for to provide strength for both imposed structural loads and also weaknesses in the soil. And the beam is supported entirely by 3 piers. So this is going to be a pier and beam foundation. Now, truth be told, it would be a bit silly to support your foundation entirely on the piers, but for whatever reason this one is, and well, that reason is just to make this contrived example, but we're simplifying the topic of foundation design. So the beam is supported entirely by piers. By 3 piers. By 3 piers, foundation piers, each positioned 12 feet apart. Each positioned 12 feet apart. And so, then an exterior pier settles 2 inches. One of the exterior piers settles 2 inches, and we're also told that the concrete of the pier has an elastic or of the both the pier and the beam. The concrete has a modulus elasticity, has an elastic modulus, of, let's say, 3.5 times 10 to the 6th psi. That's a realistic elastic modulus for concrete. Times 10 to the 6th pounds per square inch. And what I want to find is the maximum bending stress in the beam produced due to settlement. Maximum bending stress in the beam due to settlement. In the beam due to settlement. Due to the settlement. So what's happening here is I have my great big foundation pier, or sorry, I keep saying pier, I should say beam, my big foundation beam here. And this is 24 inches deep. So that's, now truth be told, this is a very deep foundation pier, although you never quite know sometimes. So this is a 24-inch deep pier, or sorry, 24-inch deep beam, and underneath this are 3 foundation piers, which are basically your, these could be drilled piers or whatever they might be, and they would go down a certain distance. Now, as far as how deep they would go, that would be a topic for a foundation design class. So I'm trying to introduce and include some materials from foundation design without actually turning this into foundation design class, but it turns out that's not going to be required for this level of analysis. And the dimensions here, let's say this is, again, 12 feet from here to here, 12 feet from here to here, and 12 feet from here to here. Center to center distance of 12 feet. And in case it's not clear, where the ground is, well, the ground is right here. This is truly a foundation. There's a building on top of this. So here's your ground. All this stuff is below the dirt, or if you ask a geocheck engineer, of course, below the soil. So all of this is below the soil. And we have this structure underneath the soil, our foundation, to support the rest of this building, whatever may be above this. But one problem is, for whatever reason, there is some sort of weakness along one of the piers. Now, I didn't specify which exterior pier matters. I just said an exterior pier, so it couldn't be the middle one, but it could be this one or this one. And really, for the sake of symmetry, it doesn't really matter. But for my example here, the way I worked it out, I decided to say it's this one here that has some level of weakness underneath it. So there's some sort of void or some weak soil underneath this pier. We built the pier not knowing this, And this, unfortunately, this pier, instead of remaining where we wanted it to, or at least uniformly settling, this one has settled 2 inches. So if you take geotech, or you take foundation design, or you study foundation design, you will realize that there is always going to be some amount of settling present, and that's not a big deal, as long as the settlement is uniform. Because if you have a uniform settlement and the entire structure just moves downward, and now that can cause problems for things like pipes, water connections, electrical connections, data connections, anything that, if you have a pipe in the soil here that then comes out and connects to the building, and the building settles downward, well, that can cause problems and maybe break a pipe or something. But in terms of the overall structural stability, that's not going to cause much issue. Where you really get problems, though, is where you have differential settlement. So if all of these together move down 1 inch in lockstep, at least marching along downward, that's not a problem. But if just one of these moves downward, then or maybe the middle one, or maybe this one, the left one and the right one move down, then that is where you'll get stress building in the structure. So in a structure, it is not a foundation settlement that produces stress. It is differential settlement. So where again one element of the foundation is settling more than another element, and that is where stress can build up. So, and that's unfortunately that is the case of what's happening here. For whatever reason, due to some weakness in the soil, this pier, relative to the others, is settling 2 inches. So, again, that doesn't mean that these aren't settling at all. But this particular one is settling 2 inches more than the other ones. And I want to know what kind of stress is going to be built up in this big foundation beam because of that differential settlement. Now, notice I'm asking the bending stress in the beam due to the settlement. To make this example is already going to be long enough, and to make things a little bit simpler, I am not asking the total amount of stress in the beam. This beam would already be supporting load above, and hopefully this wouldn't add, but it may. I think at this point you know how to linearly I'm hoping at this point you know how to add stresses, you know how to linearly superposition or simply add stress functions together, that sort of thing, add deflections together. So what I want to look at is not the total stress in the beam, but just the stress in the beam that comes from this additional differential settlement. So I'm going to ignore the weight of the structure above it, because we already know how to do that, I hope. I'm going to ignore the self-weight of the beam, because that stress is there whether you have settlement or not. I want to know how to find, or I want to calculate the settlement that comes just from one of the foundation piers settling. So if I were I'm going to simplify this into a much greatly reduced system. I'm going to represent this as a line element, and this is what my beam then collapses to. I'm not concerned with the stresses in the piers themselves. That would be a topic for another time. And let's say we have lengths 144 inches and 144 inches. And let's go ahead and name these points A, B, and C. Points A, B, and C. Let's see then. In turn, let us say we have reactions, at least normally we would have reactions AY, BY, and CY. AY, BY, and CY. And this joint here is going to move downward 2 inches. So now you may not yet see how this is going to connect with our force method from before, but if you remember in our previous uses of the force method, we have used something like this. We're going to look at joint C today. So previously we'd look at something like, okay, well, capital delta OC, or sorry, C naught I should say, if I'm going to be consistent with what I've done previously. C naught, the deflection at joint C for the primary beam, plus lowercase delta CC, the deformation at C from joint C, times CY is equal to 0. That's what we've done previously, where we said, okay, well, for a idealized pin support, the virtual versus the real must add up to 0. But in this case, we're going to say it's not 0, but equal to the level of deformation that we have, -2 inches. So, again, in our previous examples, we've assumed that all the joints are perfectly rigid. They're not going to go anywhere, they're not going to move anywhere except rotate, etc. We're assuming they're fixed immovably in space. But here we're going to say, you know what? Let's reverse that. Let's put that on its head, and let's just say, okay, well, instead of it being 0, let's give it a known deflection value, and then back calculate what kind of stresses that deformation will produce. Let's see. So again, we know that joint C will deflect downward 2 inches. We'll deflect downward 2 inches, and we'll analyze that as we discussed. So the other thing I need, let's get a few section properties, and let's discuss mechanical properties, etc. So first of all, I want to get the modulus of elasticity, the moment of inertia. We have a beam that is 12 inches by 24 inches. And I remember my statics and mechanics and materials, so I know that the moment of inertia, is equal to bh cubed over 12 for a rectangular section. Nothing that innovative there or surprising there. So 12 inches times 24 inches to the 3rd power divided by 12, and that will produce a moment of inertia of 13,824 inches to the 4th power. So nothing too bad, I hope. And then our modulus elasticity, so quite a bit of moment of inertia. This would be enormous for, say, a steel member, but of course we know this material is much weaker than steel. It has a moment of inertia, or I should probably not say weaker, I should say less stiff than steel. Its modulus elasticity is only 3,500 ksi in comparison to our usual assumed value of 29,000 ksi for steel. Now, I also want to consider what I know about redundance and things like that for the force method. I am concerned with the deformation at joint C, so I am automatically going to pick joint C as one of my redundant reactions. Now, if I had more than one redundant to choose, say I had like another pin support here or another roller support here, in that case I would want to pick this and one of the other ones. But because I have joint C as because I'm already interested in the deformation at joint C, I really have no choice except to pick joint C as my redundant. So my redundant, and thankfully I only need one redundant force here, so it's not too bad. Redundant reaction will be joint C. My redundant reaction is joint C or point C. And so then let us go on to the first step, which is to the next step, which is to analyze the primary beam. So the primary beam, this step is going to be very simple. If I can manage to not jump forward. My primary beam is going to be very simple to analyze, and you'll see why in a moment. And that's because I have my beam here. And forces, well, let's say I have AY, and BY. Well, let's think about this. Again, in my primary beam, I only retain my real loadings. Now, again, as I mentioned previously, on the actual foundation beam, we would have some, say, distributed load or the load of the structure, whatever it might be. But here, because we're only concerned with the loading that comes from the deflection, or that comes from the settlement, we don't actually have any loads imposed on our primary beam. And if you think through the statics of this, if I generate a moment about here, if I sum moments about here, that would tell me that AY equals 0. And if I sum moments about here, that would tell me BY equals 0. So there is actually no loading whatsoever on our primary beam. Both of these are equal to 0, and therefore delta CO, the real deformation caused by the loads on the primary beam, is going to be equal to 0. Alright, we have our primary beam, and now let's continue to analyze our secondary beam. So our secondary beam, as a reminder, will have the unit load imposed on it on the location we're interested in having or investigating the deflection. So let us consider the secondary beam. The secondary beam here . And for this one, because we have only one redundant, we're going to need only one single secondary beam. We don't have to do multiple like we have in some of our previous problems. So the secondary beam is going to look like this. I'm going to impose a unit load on the joint C here, or on point C. And the reason I'm going to draw this downward is because I do know that the deformation is going to be downward, so I would be basically I'm assuming, that's not a point load P, that's a 1 kip load. I know it's going to be deforming downward, and so I'm just going to predict that this force pulling it is downward. And because if you just think of the physics or mechanically how a pier settlement works, the pier is pulled downward, and that pulls the rest of the beam with it. Let's see what else. Let me show the other forces here. I will show an AY, the reaction at A, and if the 1 kip force is going to be downward, this AY has to be upward, and then BY, if I think of moments about this point, BY would have to be upward as well. And if you do a very simple balance of moments, you can find that AY is equal to 1 kip. Let's see, 1 kip. Oh, sorry about that. I have this a little backwards. That should be the opposite way. AY should be going downward, and BY should be going upward. So yeah, that's fine. So if I do a balance of moments, I will find that AY is equal to 1 kip downward, and BY is equal to 2 kips upward. And this can be explained through simple balance of moments. Okay, so I'd like to look at, ideally I'd like to get the deflection equations for this thing. Now, in previous cases, in certain times, we have been able to isolate this joint or isolate the right span and look at only its moment, shear, etc., shear moment, load, shear moment, etc. The problem with this is that if I'm looking at this secondary beam, if I were to model this, here's what it looks like. This looks like this. I have a pin and a roller. So this out here in the secondary span, this is just a free cantilever. So the problem really is that I have only one boundary condition in terms of my rotation and deflection. I know that my deflection here is 0, but I don't know the rotation at point B here, and I certainly don't know anything about the rotation or deflection at point C, so I cannot analyze this span independently of anything else. Instead, I'm actually going to have to go about this a long way and find the shear, the load, the shear, the moment, the rotation and deflection for the first span, and then use the endpoint of that as the boundary conditions for the left end of this span. So let's go ahead and do that. I'm going to analyze the first span first. So analyze the left span. And by analyze, I mean find the shear moment, rotation, and deflection functions. Analyze the left span. So let's go ahead and work through this. First of all, W is a function of X. There's no distributed load, so that's just going to be 0. No great surprise there. The shear as a function of X, if I think of this in terms of shear and bending moment diagram, in the left span, I'm going to use the subscripts 1 to refer to the left span. V as a function of X would be -1 kip. Just a constant -1 kip all the way across from here to the next span. And then M1 as a function of X. M1 as a function of X would be the integral of this, integral of V1 of X dx, or the integral of -1 dx, which will come to -x plus C1, -x plus C1, and boundary condition here. A boundary condition I can use is that the moment at the left end, because there is a pin there, is going to equal 0. So the boundary condition, m at x equals 0 is 0. That leads us to C1 being equal to 0. So my m1, my moment, in the first span, is just going to be equal to -x. It's just going to be equal to -x. No great surprise there, very similar to what we've done before. then I'm going to go ahead and get the theta as a function of x here. So theta as a function of x, theta 1 as a function of x, is going to be equal to 1 over EI times the integral of m1 as a function of x dx, m1 as a function of x dx, and that's going to come to negative x squared over 2, negative x squared over 2 plus, let's call that C2. Let's see here. And actually, let me call this one, yeah, C2 is fine. Plus C2 times 1 over EI. Times 1 over EI. And again, we don't know anything about the rotation or the slope because this is a pin and a roller. We don't know anything about the slope yet, so we're just going to go ahead and leave that as C2 for now. Then I can get the y1, the equation for the deflection in the first span. y1 as a function of x. Let's see here. So negative x squared over 2 plus C2. Y1 as a function of x then will be the integral of theta 1 as a function of x dx, and that will come to let's see, negative x cubed over 6 plus C2 x plus C3. So I need to go in and get some boundary conditions, and one boundary condition I can use is, well, let me just go through this really quickly. First boundary condition is that y1 at x equals 0 is equal to 0. There is no deflection at the left end of the beam, and that means if I plug 0 in for this and 0 in for x, I can see clearly that C3 is equal to 0. C3 is equal to 0. And then I can also plug in y of 144. y1 of 144 is equal to 0. Because of the roller support there will be no deflection at there. There'll be no deflection at y equals 144 inches. And notice I am just doing this all in inches instead of feet to avoid later conversions between feet and inches. And y1 of 144 is going to be equal to, that will come to, let's see, well, again, I do know this is equal to 0. And if you substitute in, let's go ahead and solve for this, 0 equals negative 144 to the third over 6 plus C2 times 144 plus C2 times 144. And that leads us to that C2 here is equal to, and of course my 1 over EI was just canceled out, my C2 is equal to, let's see, that would be 3,456. 3,456. So I have the following final y of x and theta of x equations. For my first span, theta 1 of x is equal to negative x squared over 2. This is again after I put in my boundary conditions, or the results of my boundary conditions, the constants for my boundary conditions. Negative x squared over 2 plus 3,456 times 1 over EI times 1 over EI. And y1 is a function of x then. Y1 as a function of x is equal to negative x to the third over 6 plus 3,456 x, again times 1 over EI. So we now have our first span completely solved for. And in the second span, I'm going to use these to connect my first span to the second span, or I'm going to use the first span's equations to get my boundary conditions for the second span. So next, let us analyze the second span. Second span. So first of all, W2 as a function of x is just going to be 0. The 2 indicates the second span. there is no distributed load in the second span, so the distributed load W is equal to 0. Then V2 as a function of x, if we go back to our diagram here, V2 as a function of x must be equal to, well, let's go ahead and solve this in case it's not clear. That would just be equal to, essentially, well, if the integral of this is just a constant, so essentially just a C1. And a boundary condition can be that at x equals 140, when x equals 288, the shear has to be positive 1, because this right-hand load is going to cause it to drop back down to 0, which means the instant before that, the shear must be at positive 1. So, boundary condition, V2 at x equals 288 is equal to positive 1. So, V2 of x is just equal to positive 1 kips. While we were at negative 1 kips prior, because initially our shear and bending moment diagram dropped down 1 here. Basically, the shear and bending moment diagram for this, it starts at negative 1, it remains constant, jumps up to positive 2, then remains constant, then drops back down to 0. Okay, so we have our shear, no great problems there. Then M2 is a function of x. M2 is a function of x. That's going to be the integral of this, which will just be positive x plus a C2. And I can use a boundary condition, and that boundary condition is, let's see here, that M1, let's go ahead and say that because there is a pin here, because there's a pin here, the pin is not going to cause any change in the moment. Only a fixed support could do that, or a moment release could do that. So any moment that is present on the left-hand side of this is going to continue right on through it. So this is not going to cause any discontinuity in the load function. So I can say that M1 at x equals 144 is equal to M2 at x equals 44, or 144. And this serves as my boundary condition for moment. And so, putting this in there, the boundary condition, or sorry, M1 here, at x equals 144, we know that M1 is equal to negative x, so negative 144 equals 144 here plus C2. So therefore, C2 is equal to negative 288. So M2 is a function of x is equal to x minus 288. M2 is equal to x minus 288. X minus 288. And then, let's see, what else? Let's go ahead and work through the deflection and rotation now, or rotation and then deflection. That'd make more sense. So theta 2 is a function of x. Let's see, theta 2 is a function of x. This, of course, is going to be equal to 1 over EI. 1 over EI times the integral of m as a function of x dx. Again, all I'm doing is repeatedly applying the equations of beam deflection that we have looked at many times throughout the semester. 1 over EI times the integral of m of x dx. And if I go ahead and put in the moment function, 1 over EI, 1 over EI times the integral of x minus 288, again dx, and then running through that integral very simply, that equals 1 over EI times x squared divided by 2 minus 288x. Minus 288x. Okay, so minus 288x. Oh, and I cannot forget my constant integration, plus C3. And, unlike in the previous case, I will not just go and solve for deflection and then back calculate C3. Here I'm going to use the, I'm going to say that, or realize that, because this is a continuous beam, and because there's not going to be any sudden changes in geometry, the rotation at this end must equal the rotation at this end, rotation must be a continuous function in beams. It doesn't have to be differentiable. In other words, the function can have abrupt changes in like slope or something, but actually no, it can't have abrupt changes in slope. I guess the function itself can have a piecewise function, but the values and slope must be constant, and even though they from one point to the next, or they must smooth, or perhaps the best way of saying it is that deflection and slope must always be smoothly changing. Anyway, getting lost in mathematical jargon. So I need a boundary condition, and this boundary condition is that theta 1 at x equals 144 is equal to theta 2 at x equals 144. Basically what this means is that at support B, the slope from the left must equal the slope from the right. So let's see here, just putting these in. 1 over EI. I'm going to put it into this function here, the theta 1 of x function. So that is then, let's see, theta 1 as a function of x, that is negative 144 quantity squared over 2. Negative 144 squared over 2 plus 3,456. And this is then equal to, if I can keep from jumping ahead, this is equal to 1 over EI. 1 over EI times 1 over EI times 144 squared over 2 minus 288 times 144 plus C3. So we have that, and what do you know, the 1 over EI cancels out. And if you have this and you gather all the like terms, multiply it together, run through all the math, you will find that C3 is equal to 24,192. 24,192. This is the one downside of using the keeping the length in inches instead of, or changing the length to inches instead of keeping the length in feet, is that some of our constants of integration can get quite large indeed. But we're not scared of that, so that's really not too bad. And then y2 as a function of x. y2 as a function of x is going to be the integral of theta 2. Again, equal to the integral of theta 2 as a function of x dx. Again, indicating that deflection is the integral of slope. So if I go ahead and run through that integral here from this, I will have 1 over EI. I'll just leave that as 1 over EI to keep things simple for now. And that's going to be x cubed over 6. X cubed over 6 minus 144 x squared plus C3x plus C3x. Oh, actually no. Our C3 is 24,192, so that's going to be 24,192 times x plus C4. Plus C4. Plus a C4 there. Okay, so we have our integral, and now we just need to solve for our C4. However, we don't need to actually use the deflection from the left-hand side for the right, because we do have one point of known deflection in this span, on the right span, and that is joint B, that has a deflection of 0. So my boundary condition here, the boundary condition for this one is that y at x equals 144 inches, or 12 feet, is going to be equal to 0. And if you do that, if you put 0 in for y of x, y2 of x, and 144 in for x, you will find that our C4 here equals quite an ugly number indeed. It's going to be equal to negative 995,328. So our final y2 as a function of x, y2 as a function of x is equal to x cubed over 6 oh, not x6, not x6 over 6, x cubed over 6 minus 144x squared plus 24,192 x minus 995,328. Oh, and of course we cannot forget times 1 over EI. So why am I doing all this? Why am I working through all this? Well, if you remember back to the idea of the force method, what I am trying to do is I'm trying to find this deflection here. I want to know the deflection, basically this here. This would be my lowercase delta cc. The deflection at joint C under a unit load applied at C, and because I have only one redundant, I don't need I'm not going to have like a BC and a CB and a BB. If you only have one redundant, you just have a single delta, just like we've looked at before. So now that I have the full deflection functions, finding delta CC is very easy. All I have to do is plug in basically x equals 288 inches into the equation that I've already calculated. So once I have this, again, I now have the entire thing, and the rest is just plugging and chugging. All right, then let's go ahead and get our final delta CC. So this here, again, all I'm doing is plugging in 288 inches into my existing y2 expression. So delta CC is equal to y2 at 288 inches, and that will come to 1 over EI times 288 to the third power over 6 minus 144 times 288 squared plus 24,192 times 288 minus 995,328, the constant we previously derived. 328, and if you plug and chug and put that all into your calculator, you will find that this equals then negative 199,000, actually 1,990,656 divided by EI. What a mess. However, oh, delta CC, not just delta C. However, if we look at this, we can then go and, so while this is a large number, we're also going to be dividing it by a large number. We're going to be dividing by the modulus of elasticity and the moment of inertia. And I'm going to go ahead and do this in KSI rather than PSI, and then I'll be aware that my final CY will be in kips. So let's go ahead and do that. That will be negative 1,990,656 divided by our E, which is 3,500 KSI. 3,500 KSI times 13,824 inches. 824, inches to the fourth, not just inches. And that comes to a lowercase delta cc of negative 0.04114 inches. 4114 inches. In other words, the unit load, a unit load of 1 kip applied at our joint C is going to cause a downward deflection of about 0.05 inches, or about a little less than a 20th of an inch. So we have our delta then, and our next step will be to balance deflections at joint C. And this is where the problem of joint deflections is going to be distinct from the other types of force method problems that we've done so far. And really it's just a slight reworking of it. So let's balance joint C. So our delta C naught plus lowercase delta cc times cy. This is very much similar to what we had previously. Now, or in the previous derivations or applications of the force method. However, in this case, it's not equal to 0. Rather, it's equal to -2 inches. We're having a deflection. This is the deflection that was observed. So a deflection, we're observing a deflection of 2 inches downward. So while we might, in the previous cases we said the deflection is equal to 0, in this case it's actually 2 inches downward. Now this delta, we already calculated this as 0, and so the rest is just actually fairly simple. We know that a unit load, it will cause a deformation of 0.041114 or 0.04114 inches times cy, and this is equal to -2 inches. So if a 1 kip load will cause this much, displacement or deflection, then how much load do we need to cause a 2-inch deflection? Again, this is linearly related for small deformations. So cy, if you divide this by this, you will get that cy is equal to 48.61 kips downward. 0.61 kips, and we did get a positive number, so what that indicates is not that it's pointed upward, that would be a bit weird for joint settlement. Rather, this means that it is in the direction we assumed. We assumed that it was downward, so that means that cy is 48.61 kips downward. And now, all that remains is to analyze the now statically determinate beam. And what we're looking for is the maximum bending stress, or the maximum settlement stress in the beam. And did I say bending stress? I believe so. Let's see, the max bending stress. Yes, there would also be shear stress and such, but I'm going, for simplicity's sake right now, I'm going to focus only on bending stress. Once you have the shear, calculating shear stress wouldn't be too difficult, but I don't want to turn this into a mechanics of materials lecture or more than it already is. So I will say instead, analyze now statically determinate beam. The now statically determinate beam. So consider the loads on the structure. I have the same points and dimensions, A, B, and C. And this is 144 inches and 144 inches. And I have now calculated cy, and this is 48.61 kips downward. 4.61 kips downward. And if you apply just basic balance of moments or basic statics, you can find that AY is equal to 48.61 kips downward, 48.61, and BY is equal to twice each of these, and that's going to be 97.22 kips upward. Now I could go and find the shear and moment via integration, but this is such a simple one, I'm just going to go ahead and find it by inspection. So, first of all, my shear is going to go like this, so V in kips. My shear is going to start at negative 48.61. .61, 61 here, and then it's going, because there are no other vertical loads, it's going to remain constant all the way over to the point B there, at which point this positive 97.22 is going to cause it to jump up to, it's going to cause it to jump up to positive 48.61. Positive 48.61. And then there are no other horizontal loads, so it will remain constant until it reaches the right-hand side of the beam, where the reaction will cause it to drop back down. And again, this is 144 inches and 144 inches. Now I would like to get the areas of these. That will be useful for calculating my moment. And that the area of this piece here, area is just going to be equal to 144 times 48.61. And that comes to 7,000 kip inches. So I know that the area of each of these is 7,000, and that'll allow me to very easily get my moment diagram. Let's see here. Again, that'll allow me to very easily get my moment diagram. And let's just put M in kip inches. And let's just finish this problem out. Between A and B, there's going to be an area of negative 7,000, so that will mean the moment will drop down to negative 7,000, dropping down linearly. Negative 7,000. And then the positive 7,000 will bring it back to 0 towards the right end of the beam. So we do have negative bending throughout the beam, so this is sad-faced bending, or downward bending, or negative bending. Negative bending moment throughout, and I also now know that the M max is equal to 7,000, or negative 7,000 kip inches. So at this point, it's very easy to find what I was asked for at the beginning, and that was the maximum bending stress from settlement. And so sigma max is going to be equal to simply MC, if I go back to mechanics and materials, the max bending stress for a linearly elastic beam is just going to be equal to M max or times C divided by I, assuming everything's below the elastic limit anyway, times C over I. And so this is going to be 7,000 kip inches times C of 12 inches, that's the distance to outermost fiber, divided by I, your moment of inertia, distance from outermost fiber, again from the neutral axis to the outermost fiber, if you want to go back to some mechanics and materials topics. And the moment of inertia I is 13,824 inches to the 4th power. And putting that into a calculator, you will find that the sigma max is equal to 6.08 KSI. And that 6.08 KSI is our ultimate maximum bending stress produced by settlement in this beam from the right pier settling 2 inches. And of course, there would be other stresses present in the beam. As we mentioned at the beginning of this problem, we were interested in just the stresses that are produced by the pier settlement. So I hope you've enjoyed this, and I hope you found this a bit illuminating. This is, again, just another application of the force method to beams. So I just wanted to provide this to illustrate how flexible the force method can be as a tool for analyzing statically indeterminate structures. So we have seen that we can use it for all sorts of applications, whether we're looking at just solving single-span beams, or solving statically indeterminate beams, or deriving equations to derivation, and now even finding pier settlement and foundation settlement problems via an imposed deformation, and calculating the loads associated or stresses associated with imposed deformation. So we can see here that the force method really is an extremely versatile tool for analyzing statically indeterminate structures. Alright, well, thank you for joining me this evening. I hope you all enjoyed this. Hope you all found this a bit illuminating. I'll see you all again next time. Thank you for watching, and as always, thank you.